Welcome at last to our course on Mechanical Behavior of Materials Part 2. So in the last class, we discussed the concept of fracture toughness. We talked about the uh, concept of plane strain fracture toughness and plane stress fracture toughness. And I also mentioned that, fracture toughness value will depend upon the thickness of the material. So at a certain thickness, higher thickness value, your fracture toughness value will become constant, relatively constant, and that value is called plane strain fracture toughness. And in this course, we will be using K1C as plane strain fracture toughness. Okay. I also mentioned that we will be using a HTM standard, which is E399 to measure the plane strain fracture toughness. So today we will talk about how to measure plane strain fracture toughness in metallic materials. Okay, let's begin. So we will talk about today plane strain fracture toughness testing. Okay, so for that we'll be using ASTM E399. Okay, mostly for metallic materials. And here I also mentioned in the last class that fracture toughness under predominantly linear elastic and plane strain condition. Okay, so we'll talk about E399. So to do that, we'll be using compact tension, which is CT specimen. So we have already discussed the configuration for compact tension, right? So how does it look? So you are going to have a specimen like this. With certain thickness. Okay. And this thickness is denoted by B. And how do we measure the crack length and the width? So that will be measured from the center of the pin. So remember, compact tension is pin loaded specimen, right? So this is the center of the hole here in the sample. So your crack length will be measured from this particular point. So W is this. Okay. And this one is your notch, which you can make using EDM. Okay. Electrical discharge machining, or in some books you will see electro discharge machining. Okay, so you can use that and make notch. So before we do this fracture toughness testing, we have to pre-crack the specimen. Okay, so we have to generate some crack. So it can be either natural crack or you can actually do fatigue testing to generate pre-crack here. So this is your pre-crack. Okay, so from the notch, you are generating a crack. Okay, because I have already mentioned that whenever you use fracture mechanics, we talk about cracks. Okay, so you are generating a pre-crack using fatigue cracking, and now the crack length can be measured from the center of the specimen. So this becomes your crack length here. Now, when we do this test, we measure load versus CMOD. What is CMOD? CMOD is crack mouth opening displacement. Okay, so P, which corresponds to load, and CMOD, it's small d. Okay, so load because you're doing the test, so you have a load cell in the machine, so you know what is the value of load. You have to now figure out what is CMOD. Okay, and then we'll plot P versus D. I will show you how the plots are going to look like for different kind of materials. Okay, to measure CMOD, we use, so CMOD is what? Crack mouth opening displacement. So you are actually going to measure the displacement here. Okay, so if this is your crack, what is the displacement in this particular point? Okay, so how much your crack is getting opened when you apply load? Okay, so that is what crack mouth opening displacement. To do that, you use clip gauge. So you fix clip gauge at the end here at these points. Okay, and when you apply load, there is a tension, and you can measure what is the crack mouth opening displacement. Okay, so basically our outcome of the test will be P versus D, and we are going to plot that. Okay, so when you plot, you are going to get load versus displacement, where P is your load and displacement here is CMOD. Okay, so we are going to have three type of plots. Okay, so the first one will look something like this. So P, and then here you have D. Okay, so this is type 1. The second one is something like this. Okay, so again P versus D. This is type 2. And the last one is just goes like this, and then okay, so P versus D, and this is type 3. So these are the three types of curves you are going to get, and these are based on ASTM 399. Okay, so now I will introduce a concept of P max, P5, and PQ. Okay, so these are the three terms we are going to use in these plots. And finally, we will get PQ, which can be used to something called provisional fracture toughness. And there are some criteria with respect to, the variables like B, crack length, etc. To determine the plane strain fracture toughness. Okay, we'll talk about it. So let me explain what is Pmax, P5 and PQ. So Pmax, it's the maximum load you are going to get in a certain plot. Okay, so if I just see plot 1, so this becomes your Pmax. Okay, in plot 2, this particular point is Pmax, and in plot 3, this is your Pmax. So Pmax is simple. That is a maximum load in the given plot. What is P5? So let's talk about P5. So that will be, to figure out, you have to draw 5% second line, which is a line from the origin with a slope equal to 95% of the initial slope. Initial elastic loading slope. Okay, so to find out P5, what you have to do, you have to draw a 5% second line, which is the 95% of the initial slope corresponding to the elastic curve. We'll do that. Okay, so that is P5. Now, what is PQ? So to calculate PQ, there are conditions. So if the load at each point on the plot which precedes P5 is less than P5, okay, then PQ will be equal to P5. Okay, and in other words, we can write load value at each point should be lower than P5. Okay, so it means that if we are in a particular plot, and we'll do that. So eventually you are going to learn while seeing the plot. So if the load at each point on the plot, which is before P5, is less than P5, then PQ will be equal to P5. Okay, that means that the load value at each point in the plot should be lower than P5. If that is the case, then PQ will become equal to P5. Now, case 2, if load at any point is higher than P5, then the higher load value will correspond to PQ. Okay, and let me now just point out that this condition A will correspond to type 1 curve and condition 2 will correspond to type 2 and type 3 both. Okay, so if the load at any point is higher than P5, then the higher load value will correspond to PQ. Now let's use these three curves and calculate P5, PQ, and Pmax you already know. So we'll do one by one. Okay? So let's do for type 1. So type 1 plot is T versus T, and the plot is something like this. Okay. So now let me draw the initial slope because we have to figure out P5, right? So let's see initial slope is something like this. So this becomes your initial slope. Now I have to draw P5. Okay, so let's see, this is O and then we are drawing OA. So OA is slope of say elastic line. Okay, now we have to figure out P5 which corresponds to the 95% of the slope of the elastic line. So that will correspond to, so we are now drawing 95% of the slope. So let's say which is something like this. So this particular point now will correspond to P5. Okay. And now we can write OP5. So this particular line OP5, this is second line through origin. Okay. Having slope that is 95% of OA. Okay, or 5% less than OA. Okay, so remember that is how we wanted to calculate P5. Okay, 5% or 95% of the initial slope, wherever it touches the load versus displacement curve, that particular point or that particular load will correspond to the value of P5. Okay, now this particular curve is like, you know, PD. This is curve is smooth and it deviates slightly from linearity before reaching to the maximum load. So this is the nature of this particular plot. It is smooth and it deviates slightly from linearity before it reaches to the maximum load, which is in this case is this Pmax. Okay. Now, if you remember, how do we calculate PQ? So we have to note down the each load value and see if it is less than P5, right? Then we will say P5 becomes equal to PQ. Okay, so let's do that. So let's start from the origin. Okay, so let's start from origin. So we will start from this particular point and we'll move along this direction in the curve itself, in the purple color. Okay, so we are moving along this direction like this. Okay, and then all the load points till we reach to P5, those points are less than P5, right? So that means P5 in this case in type 1 curve will become equal to PQ. So for type 1, P5 will become equal to PQ because all the load points, all the load values are less than P5 before we reach to P5. Okay, so this is type 1 and the characteristic is this, the non-linearity here. This can be caused because of plasticity, local plasticity. So non-linearity can be caused by plasticity or subcritical growth or both of them. Okay, so remember for type 1, P5 becomes equal to PQ. Now let's say what happens when we have type 2. So if you remember, the type 2 curve is going to look something like this. So P and D, okay. Then it goes, then there is a popping, and then it goes up. So now we know at least this value as P max. This much we always know, right? The maximum load in the particular plot is P max. Okay. So now let's draw first initial slope. So let's see, initial slope is something like this. So this is your initial slope. Now to figure out P5, we have to draw 95% of OA, right? So here we have O and this line is OA. Okay. So now let's draw P5. So we have to draw 95%. It will be something like this. Okay. So this becomes P5. Okay. So now we know OA, which is the linear curve. OP5 is the second line, which is having a slope that is 95% of OA. Okay. Now, what do you see? There is small drop, right? That is called popping. So what you observe here is a small amount of unstable crack growth, which is popping before curve deviates from linearity by 5%. Okay, so you see there is a small amount of unstable crack growth which is corresponding to popping. So we are talking about now this particular region here. Okay, and it happens before you see a deviation by 5%, which is O5. So you see that happening there. Okay. Now, so what is PQ here? So to calculate PQ, we have to now start from origin and move upward in the load versus displacement plot and see if all the load values are lower than P5 or not. If it is lower than P5, then we can say that P5 will be equal to PQ. If not, then the higher value will correspond to PQ. Okay, so let's do that. So we will again start moving from this origin and we will move on the curve, purple curve like this. So all values are lower than P5. Okay, till this point. Now I am on the top point here. So you see that this particular value on the top, right? That is not lower than P5, that is higher than P5. So now the top value or the starting of popping will correspond to PQ. That was condition B, if you see. Okay. So we are now talking about this particular point number B. So if load at any point is higher than P5, then the higher load value will correspond to PQ. And I already mentioned that the type 2 and type 3 will be like that. So you see here that the PQ value, the highest point here is higher than P5, right? So here P5 is not equal to PQ. PQ is that particular load. So let's denote that say as C. So if I denote this particular point as C point, okay, so C will correspond to PQ. So the load value at C will correspond to PQ. Okay. And what is PQ in this case? This is popping load, where popping starts. Okay. And also remember, PQ is higher than P5 in this case. Okay. So this is type 2, where PQ is not equal to P5 and PQ is higher than P5. Now let's come to type 3, the last one. So that will have P and then D in this direction. Okay. And this was much simpler than the other. So it just goes like this. And then, so Pmax we know. So this particular point here is Pmax. Okay. Now let's draw the original slope. So O, so original slope will be OA. So this is initial slope. Okay. Now let's draw P5. So 95% of the slope value, initial slope. So will be something like this. Okay. So now wherever it cuts, that point is P5. Okay. So now you can see P5 is lower than Pmax. Okay. And here the characteristic is like the specimen fails completely before achieving 5% non-linearity. Okay, so before it sees 5% non-linearity, the specimen fails. That is what you see in this particular plot, correct? Now we have to calculate PQ. So to do that, we have to again move from the origin, row upward in the purple curve, right? So we'll start from this particular point and now we'll move. So all now we have to note down the load values. So all these yellow dots, these load values are till now lower than P5. Okay, but we reach to a value which is the highest one before it reaches P5, right? So the second condition, condition B, is now valid. So let me now denote this particular point, the P max, as point C. So this will become equal to PQ. Okay. So now you know if the plots, these three plots are given, how do you calculate the initial slope? How do you calculate P5? And finally, how do you calculate PQ? So in this case, PQ is going to be equal to P max. Okay. And as usual, P max is greater than P5. So if this case is not valid, then P max will be equal to PQ. If all the points are less than P5. Okay. Sorry, PQ will be equal to P5 if all the points are less than P5. Okay. So now we have discussed the three types of curves given in ASTM standard. We can calculate now PQ value. Now this PQ will be used to calculate the provisional fracture toughness. And provisional you means, you know, right? It is like your degree. So unless you satisfy all the degree requirement, you get provisional degree certificate, right? So same thing here. Unless you satisfy a few criteria for fracture toughness to be called as plane strain fracture toughness, we will have the value of KQ, which will correspond to the load value of PQ. And once the criteria is satisfied, KQ will become equal to K1C. Okay. So let's now do that. What are the different criteria for that? So since we are talking about compact tension, we know the formula of K, right? So K Q we can calculate from PQ, and then F A by W. Okay. What is KQ here? KQ will be called as provisional fracture toughness. Okay. And we are calculating this. So we are calculating KQ from PQ value from load versus displacement curve, right? Okay. This is compact tension. You know the formula for FA by W. We have done that. You know A, you are doing the experiments. You know what is A, you know what is W, you know what is the thickness. So all the parameters here, you know, right? PQ, you need to calculate from P versus D plot. So you know PQ, you can calculate KQ. Okay. Now, if KQ to become wants to become or KQ to become K1C, which is plane strain fracture toughness, we have certain criteria. So these criteria needs to be fulfilled. So what are the criteria? This KQ will be equal to K1C if A by W is between 0.45 to 0.55, then B and A should be greater than equal to 2.5 times KQ sigma ys square. And the last one is the Pmax value, right? That should be less than 1.10 PQ. So if all the three criteria are valid, then the calculated value of KQ will be given as plane strain fracture toughness KQ, K1C. So if all these are valid, then KQ will be K1C. Okay. And if these are not valid, then you have to increase the specimen thickness, because we know that if these are not valid, and if you remember that the fracture toughness varies like this, so it might be somewhere here, right? So you have to increase the thickness value so that it goes to the region of plane strain fracture toughness. Okay. So this also means, you need to know a rough estimate of K1C, right, to determine what could be the thickness. Because if you don't know the thickness, how do you perform the experiment? So some idea of fracture toughness initially will be useful to determine what could be the initial thickness, and then you perform all the experiments. If it is not the criteria is not getting validated, then you increase the thickness again and then see whether the criteria is again getting validated or not. Okay, so remember that these three criteria should be valid for KQ to be called as K1C. Okay, and if you see this terms, you can correlate this with respect to your plastic zone size. Okay, so this is coming because we are having a condition of linearity, right? The plastic zone size should be much smaller than the other dimensions. Okay, so now let's do some numerical problems to understand the concept more clearly, especially in terms of the requirement of this different dimensions of the specimen. Okay, so let's see examples. So you have a steel, so condition A, sigma ys given as 350 MPa. Okay, and you need to calculate specimen dimensions required for a valid K1C test. Okay, K1C is also given as 200 MPa root meter. Okay, so steel material is given and its yield strength is given as 300 MPa. So you have to calculate the specimen dimension so that K1C is valid. Now, what is the criteria? So B and A has to be greater than equal to 2.5 K1C divided by sigma y square. So this is one of the criteria, right? So let's use that. And if you just calculate, you place the value of K1C. So 200 divided by 350 square. And if you calculate, it will come out to be 0.816 meter, which is 82 centimeter. Okay. And again, one of the requirement is say 0.45 less than A by W. So A by W should be between 0.45 and 0.55. Okay. So let's assume that A by W is equal to 0.5. Okay. So A will come out to be 0.816. So for say minimum A. So remember B and A has to be greater than this value, right? For K1C to be valid. So let's take the minimum value of A, which will be 0.816 meter. And if you use this particular value of A, W will come out to be 0.816 divided by 0.5. So it will be 1.63 meter. Okay. Now, what is the value of thickness? In the range of meters, right? Similarly, width is in the range of meters. So, sometimes if you want to calculate the plane strain fracture toughness, it is very, very expensive. Sometimes it is impractical because of the stringent requirement of these criteria. The sample dimension becomes so huge that you have to have lots of materials which needs to be cut, or you have to design a special machine so that you can actually have tasted or actually can taste all these material with such a large dimension, because the load requirement also goes up. Okay, so sometimes it becomes very difficult to follow this standard because of the stringent criteria in terms of the dimensions. Okay. So this is point one to note. Now let's do the another example. So in this case, you know that it is difficult. Huh? So case B. Now let's see that B is 25 millimeter somehow. In the above example, B is 25 millimeter. We have that specimen. So let's calculate what could be the largest possible K1C for a valid test. So what I am saying that we have now fixed the dimension. Okay, previously we calculated the dimensions from the given material properties. Now let's fix the dimension and see what could be the maximum K1C of a material we can have for this particular test to be valid. Okay, so there now we will are going to have constraint in material now. Okay, so B and A, we know the requirement is 2.5 K1C by sigma y square. Okay, so sigma y we will assume the same as before. So sigma y was 350. Okay, so if you do that, K1C will come out to be less than equal to 35 MPa root meter. Okay, so if the thickness of the material is 25 millimeter, right, yield strength of the material is 350 MPa, so the maximum K1C for that particular material should be less than or equal to 35 MPa root meter, so that this ASTM E399 will be valid. Okay. So this is the another problem. Now let's do one or two more. So now let's talk about aluminum alloys. And for aluminum alloys, especially age hardenable alloys, you might be knowing that depending upon the aging treatment, the precipitate characteristic changes, and that will lead to different strength of the material, right? Remember the precipitation strengthening mechanisms we discussed in our course 1. Okay, so let's use that concept of precipitation hardening and see how the strength changes, right? And then how this criteria is going to be validated there. So we will now talk about example of aluminum alloy. So you have been given A equal to 4 centimeter, B equal to 1 centimeter. And now you are talking about aluminum alloy, which is 7178. Okay, so it's 7 series aluminum alloy. And we are using two tempers. One is 7178 T651 and another one is 7178 T7651. So one is the P cased, so this one is your P cased. And this one is towards the higher side, so overaged. Okay. So K1C in these two conditions are going to be different. 23.1 and the other one is 33. Similarly, sigma ys is going to be lower in overaged. We know that based on the hardness plot. Remember, just realize what we discussed in course 1. So it is in MPa and this one as usual is in MPa root meter. Okay. So 570 and 490. So these are different tempers. Okay. So two different tempers of aluminum alloys. So the question is, will the above dimension of the specimen would lead to valid K1C? So we have been given dimension as A and B. The values are given. We know what is sigma ys. K1C is also given. So we have to see whether this dimension of the compact tension. So this specimen is again CT. Will this lead to a valid K1C? Okay. So let's do that. So first for 7178 T651, we'll do that this alloy. So what is the criteria? B and A should be greater than 2.5 K1C by sigma y square. Okay. So if I just place the value of K1C and sigma y, this will be 23.1 and sigma y is 570 square. It will come out to be nearly 0.4 centimeter. Okay. So B and A in this case should be equal to or say greater than 0.4 centimeter if K1C test is valid or this value is also valid, right? And see the given dimension is A is 4 centimeter and B is 1 centimeter, right? So both are greater than 0.4 centimeter. So yes, the dimensions are okay. It is going to be valid K1C test if we use these dimensions for compact tension specimen. Okay. Now so this is A. Now let's do for the another alloy. So 7178 T7651. Okay. So same procedure. So BA has to be greater than 2.5. What is K1C here? It is 33 and sigma y is 490 square. Okay. And if you do that, it will come out to be nearly 1.1 centimeter. Okay. Now A is 4 centimeter. Very good. It is greater than 1.1 centimeter. But see B, the dimension is only 1 centimeter. But if the test has to be valid, B has to be greater than equal to 1.1 centimeter. So the criteria for B is not getting satisfied in this case, right? In the second alloy, T7651. So here dimensions are not okay. Our dimensions will not provide valid K1C test. Okay. So this is another example of the requirement of dimension for K1C test to be valid. Okay. Let's do one more. So let's consider a hypothetical case where you have CCT plate infinitely large, and then the applied stress is sigma d. So we are assuming a hypothetical service condition okay, where you have screw thickness, crack of 2 length in infinitely large CCT specimen, okay, and sufficiently thick to develop plane strain condition. Okay, so we are assuming the plate, okay, a CCT plate having track length 2a, which we already know. Okay, and the thickness is sufficiently large so that the condition is good. Plane strain condition is valid. So whatever K1 K value we calculate using the HTML standard, that will be K1C. Okay. Now let's assume that the applied stress is half of the sigma ys. So we are applying the stress which is half of the field stress. This is a CCT specimen, infinitely long, large, right? So we can write K1C as y sigma root pi a. Y will be equal to 1 because this is infinite plate. So this becomes sigma root pi a. Okay. And we are calculating AC value here, which is the critical track length. So we have done something like this in the last lecture also. Okay. So we are trying to find a critical track length. We are trying to find out the critical track length AC. K1C is given. Sigma is sigma ys by 2. So let's do for different materials. I'm going to make a table now. So you have material K1C. Since the condition is valid, sigma ys and the corresponding value of AC from the formula. So if you use K1C sigma d root pi AC, right? So K1, whenever we have K1C, it will be either critical stress or critical length, right? So sigma d is given, that is the design stress, which is half of yield point. So we have to calculate what is AC. So if you know K1C, we know sigma d, we can calculate AC. That is what we are doing here. So we have different material 2014 T651. K1C is given as 24.2, 455. So AC, if you calculate, it will come out to be 3.6. Okay. So this is from the book of Herzberg. This is 44, 345. And then if you calculate 21. Okay. Now let's do 7075 T651 24.2 495 and then 3 millimeter. 7178, which we already did, right? 23.1 570 will come out to be 2.1. Now titanium alloy, there's 11.115.4 910, so 20.5. Then we are now in steel 4340, then 177 pH. Then we have say H11 and then 350 marathon steel. The values are 98.9, 76.9, 38.5, 38.5. Yield point values are 860, then 1435, 1790, 2240, and these values are 16.8, 3.6, less than 0.6, less than 0.4. Okay. So if you see the requirement of AC, right? And the one thing you need to know that as you increase the strength, so this table, you know, very nicely. So depending upon the material, obviously the yield strength is going to change, right? So this table shows that as you are increasing the strength, the requirement for the critical crack length is going to be much smaller. Okay, so this is the 350 marathon is still the requirement of the critical crack length, which you can measure, right, or which you can detect is very, very small, 0.4 millimeter, right? So as soon as it reaches 2.4 millimeter, your sample is going to fail. So that is what this table suggests. Okay, let's do one more quick problem and then we'll close this class. So now assume a component. You are going to make a component from 0.45 C nickel chrome moly steel. Okay, and it is required that the critical flaw size be greater than 3 millimeter. Okay, so you are going to make a component of this steel, okay, carbon nickel chrome moly steel, and the critical flaw size requirement is that it has to be greater than 3 millimeter, because the equipment, say whatever we are going to use, can detect only up to 3 millimeters. That is the requirement we have for this particular problem. Okay, so the resolution limit of the equipment we have. Now design stress sigma d is again half of sigma, say tensile strength now. Okay. Now to save weight, I'm making a statement and then we have to see whether this is going to be valid or not. To save weight, increase in tensile strength from 1520 MPa to 2070 MPa is suggested. So the question is such strength increment allowable? Okay. So we are making a component of the given steel. Flaw size, I already mentioned that it should be maximum 3 millimeter. Design stress is given. Now I'm proposing that if you want to increase the, if you want to save the weight, the tensile strength should increase from 1520 MPa to 2070 MPa. Okay. So the question is, can we do that? Can we increase the strength given the condition of say design strengths as well as the flaw size limitation? Okay. So you have been given one plot where K1C is going to be changing with tensile strength and it is going down. Okay. So depending upon the tensile strength of this given material, we know what is going to be the K1C value. It is going down as we increase the tensile strength. Okay. So let's solve this quickly. So this is also very simple problem. You have been given K1C because you know the tensile strength. So you have to use the plot. Okay. So K1C is known, you know what is sigma D, right? Because the tensile strength is 1520 or 2070. So you have to calculate A value. Okay. So case 1, where tensile strength is 1520 MPa. So sigma D is, you know, it is 1520 by 2. Okay. Now at this particular value of 1520 MPa, so let me just give, so this is from one of the paper, this data. So we know some values here and some range is given in between. So for tensile strength of 1520, we know the K1C value is 66 from the plot. Okay, now let's use K1C equal to sigma D root pi A. Okay, so from here, you know what is sigma D, you know what is K1C, you can calculate A and that will come out to be 2.4 millimeter. Okay, and since we are talking about now CCT here, so 2A will be 4.8 millimeter. Okay. So the track length is coming out to be 4.8 millimeter, which is greater than 3 millimeter. So yes, this is valid here that 1520 MPa is fine. Okay, and we can detect the crest size this so that it doesn't fracture. Right? So we can detect it. Now let's talk about case 2. Sigma tensile is given as 2070 MPa. And from the plot, we know that K1C value for this is 33 MPa root meter. Okay. Sigma D here, the applied stress or design stress is half of tensile strength. So this. Now we can use K1C again. The formula sigma D root pi A and 2A will come out to be 0.65. So let me write AC here, because we are talking about critical because we are now using K1C. Okay, millimeter. So if we increase the strength from 1520 MPa to 2070 MPa, the critical crack length requirement is going to decrease. That we also got to know from the previous table, right? So the decrease, it decreases the critical crack length and now it is 0.65 MPa. Our equipment cannot detect it, right? So your material can fracture, you're not able to detect it. So the question was, is such strength increment allowable given the condition here? So the answer is no, it is not allowable because the critical flaw size, what we want to be detected should be greater than 3 millimeter. And in the case 2, increase in the strength by 2070 MPa, it leads to a track length of only 0.65 MPa, which is lower than 3 millimeter. Okay. So in this class, we have discussed about the determination of plane strain fracture toughness. Okay, and we have done some problems so that you can understand the concept of fracture toughness. It's used in the design of different components. Okay, so I will stop here and we'll meet in the next class. Thank you.